Hello, I'm Ben Manning, and this presentation is over the jetting process, which covers Chapters 7 and 8 from Additive Manufacturing Technologies. Specifically, I will be discussing material jetting and binder jetting. What makes material and binder jetting similar is through the deposition of a material to create a desired part. Material jetting achieves this through the deposition of a liquid material dispensed through a print head, while binder jetting only utilizes a small amount of material through the print head and uses more powder material and resin. On the subject of material jetting, it can trace its roots to the 1960s through inkjet printing, which is still common today. Three-dimensionally, this method was first introduced in the 1980s through the development of ballistic particle manufacturing, where a flow of a material is ejected through a small orifice and placed on a surface using a kind of mechanism like an inkjet. The first models to print in 3D used heated, waxy thermoplastics. However, more recent devices have started to use acrylic photopolymers, where upon deposition, droplets of liquid monomer are formed and then exposed to UV light to promote polymerization, meaning that under this light, the monomers will take shape and solidify. While the use of acrylic photopolymers seem to be the most popular for material jetting, there are several materials that can be used. Other than the fact that it is one of the only commercially available materials for material jetting, the popularity of polymers is likely due to its viscosity. Commonly, the maximum printable viscosity is around 20 to 40 centipoise, which is the equivalent unit to millipascal seconds. However, high viscosity liquids can negatively affect droplet formation and clog nozzles. A solution to lower viscosity would be to simply heat the liquid, but this can negatively affect the machine components if heated too high. Another solution would be through solution and dispersion based deposition, which utilizes a carrier liquid with adequate viscosity that contains a solid or high molecular weight polymer. Ceramics are a material like this. Ceramics, when used, have shown to have some success in printing through the use of this liquid carrier with moderate viscosity. However, high concentrations of the suspended powder can make the viscosity too high to print. Also, the parts yield only partial ceramic density. Therefore, the green part will need to be burnt out and sintered, making it susceptible to shrinkage. Furthermore, the low concentrations of polymer and solid within the solutions and dispersions can restrict the amount of material that can be deposited. Also, it can be challenging to control the deposition pattern within the impact of the droplet, though this setback can be handled through control of the droplet drying conditions. Lastly, the main issue with this technique is the use of more volatile solvents can result in premature formation of precipitation within the nozzle and cause clogging. Finally, metals are another material that has potential in material jetting. However, their usage at the moment is limited to primarily electrical applications, specifically the forming of traces, connections, and solderings. Though significantly less common, there is some work into the 3D aspect use of metals. Copper, aluminum, tin, and mercury are such metals that have been tested in printing to some degree of success. Unlike ceramics, these metals that are printed using material jetting have high density and uniform microstructure. Material jetting technology commonly falls under two categories: continuous stream and drop on demand. Continuous stream has a steady pressure applied to the fluid reservoir, which allows for a column of fluid to be ejected. This stream then forms into droplets through Rayleigh instability and can be controlled through vibration at a fixed frequency. To create constant intervals, the droplets are formed and introduced to a charging field and given an electrostatic charge before passing through a deflection field, which then directs the particles to the desired destination. This results in the formation of droplets of equal mass and equal intervals. For drop on demand, individual droplets are made in the nozzle directly and are formed when independent pressure pulses in the nozzle cause the fluid to be expelled. To create these pulses in pressure, various types of actuators are used. The two main actuators used, however, are piezoelectric and thermal, otherwise known as bubble jet. The thermal actuator uses a resistor to heat the liquid until the bubble forms within the reservoir, which forces the droplet out, while piezoelectric actuators get the droplet out through the reliance on the deformation of a piezoelectric element to reduce the volume in the reservoir. As with most manufacturing processes, material jetting is low cost, high speed, easy to scale, and can easily build parts in multiple materials, with an added benefit of being able to print in color. However, there's a limited number of materials that can be used at the moment, with only waxes and polymers commercially available. Also, part accuracy does not compare well with other processes, and is especially true with larger components. Now, with binder jetting, unlike material jetting, this prints a binder into a powder bed to create a part. Thus, only a small amount of the part material is printed through the print head. The binder droplets, when printed, form a collection of binder liquid and powder particles and bonds to the previous layer. When a layer is completed, the powder bed is lowered and another layer of powder is spread and is repeated until the part is complete. The completed part is then commonly left on the bed until the binder is fully set and the green part is fully strengthened. The part is then separated from the bed, any excess powder is removed, and the part is infiltrated to make it stronger as well as give it other mechanical properties. Commercially, there are a lot of materials available for binder jetting. Currently, plaster base, PMMA, metals such as stainless steel or bronze, or sand powders with wax, polymer, or water-based binders are just a few of the materials available commercially. However, these parts can be weak, so they will need to be infiltrated with another material. Fortunately, there are a variety of infiltrants available commercially and can range from a simple acrylic-based infiltrant to a more complicated two-part infiltrant. For the creation of the metal part, however, the green part must be removed from the machine and then placed on a furnace 3 times, at least. The first time, it is at low temperature for several hours to burn off the binder. The second time is at high temperature to lightly sinter the particles together and strengthen it. For the final time, a bronze ingot is placed touching the part so that it is infiltrated within the part's pores, increasing its density. There has also been a lot of research into ceramic materials in the binder jetting process. Ceramics follow a similar fabrication process to metals. Green parts are exposed to thermal decomposition before sintering to remove the binder. Then they are sintered and infiltrated. Early setbacks that were encountered were due to the use of dry powders, which did not flow well. To counteract this, a slurry-based working material was used. Layers are first deposited through the use of an inkjet printing a layer of slurry over the build area. The slurry then dries, and the binder is selectively printed to create shape and then repeated as necessary. Now, most common binder jetting machines use the same design. However, there are differences in the plaster and polymer powder machines to the metal and sand machines. The plaster and polymer machines are generally lower in cost, and their containers for the powder are small enough to be carried by hand. In contrast, the metal and sand machines have containers that weigh hundreds to thousands of pounds and are more costly. These large machines then have a rail system for moving powder beds to and from depowdering stations, and large equipment like cranes are used in moving the created parts. There have been plenty of discussion about continuous printing or mixing parts together larger than the additive manufacturing machine within the community. One such approach, commercialized by VoxelJet, utilizes an inclined plane at an angle of 30 degrees, which is small enough for the powder to not be affected. The recoating and binder jetting are actually done at this angle, and the powder bed moves from the front to the back, which is the opposite of what normally happens within this kind of system. The parts produced have the ability to have any length required, infinite if you desire, without any limitation from the size of the machine. The second approach utilizes a circular powder bed with constant rotation and continuous binder printing and recoating. While in motion, the powder bed moves down the spiral continuously to make room for the next layer. Moreover, the top layer forms a spiral in the powder bed. There are also several build stations that each contain a print head of multiple nozzles. A side effect of this design, however, is that the print must be pre-skewed to compensate the differences in speed from the outside and inside of the powder bed. Benefits and drawbacks of the binder jetting is that it shares, benefit-wise, it shares many of the same benefits that material jetting has, with some distinctions. It can be faster since less material is going through the print head. Binder jetting allows for combinations of powder materials and additives that would generally not be possible or extremely difficult for other direct methods to produce. The addition of slurries with higher solid loadings are possible with binder jetting, allowing for better quality ceramics and better metal parts to be produced. However, the need to distribute powder adds another step to this process, which can slow it down, and parts from binder jetting processes also tend to be a little less accurate and have poorer surface finish than material jetting once you get small enough. Material jetting and binder jetting share as many differences to each other as they do similarities. While they both require the use of a print head to deposit a material onto a substrate, binder jetting only subjects a small portion of the material through the print head, while material jetting uses all of the material through the print head. Material jetting also uses a liquid material, while the binder jetting incorporates more of a powder material and a binder/resin. There is a much broader range of materials that can be used in the binder jetting process, while material jetting can be limiting. However, especially for smaller parts, material jetting is more accurate and has a better finish. The binder jetting process is more suited for ceramic and metal parts. Material jetting uses more polymer materials. Both processes are relatively low cost, low energy, and commonly non-toxic, with the added benefit of being able to print in color. Therefore, both jetting processes demonstrate that, while very similar, they have individual strengths and weaknesses and can be used to create a variety of parts. Resources: all figures came from the Additive Manufacturing Technologies by Ian Gibson, David Rosen, and Brent Stucker. Thank you for your time and have a lovely day.